Chapter 14, Self-Assessment, Question 10, page 660 by Heng Yang.
Question 10 states, the rate constant for a reaction at 25 degrees Celsius is 0.01 seconds to the negative 1, and its activation energy is 35.8 kilojoules. Find the rate constant at 50 degrees Celsius. In this question, we are asked to find the rate constant of a reaction at a different temperature using the Arrhenius equation. Here we have the Arrhenius equation. K stands for the rate constant for a reaction. A is the collisional frequency factor. EA is the activation energy in kilojoules per mole. R is the universal gas constant, which is 8.314 joules per mole K. And T is the temperature in Kelvin. Here's the natural log form of the Arrhenius equation. We have two different rate constants since we have two different temperatures. The two equations can be put together in this form to determine K from the two different temperatures. The question asks us to find the rate constant of a reaction after a temperature change. We use K2 to represent the rate constant after temperature change. We can take the natural log on both sides of the equation to get rid of the ln. Then we can multiply both sides of the equation by K1 so that K2 stands on its own. Now, going back to the question, we can make a shopping list of the important information we will need to plug into our equation for K2. We know that the initial temperature of the reaction is 25 degrees Celsius. At the initial temperature, our rate constant is 0.01 seconds to the negative 1. We want to find K2 after the reaction temperature increases to 50 degrees Celsius. The activation energy for the reaction is 35.8 kilojoules, and our gas constant is 8.314 joules per mole K. It's important to convert our temperature to Kelvin and energy to joules to cancel out the units in the gas constant. Now that we have all the information we need to plug into our equation for K2, we can solve for K2 and we get 0.031 seconds to the negative 1. This is our rate constant at 50 degrees Celsius. To summarize, we were asked to solve for the rate constant of a reaction after a temperature change. We used the Arrhenius equation in its natural log form to solve for K2, and we found that the rate constant at 50 degrees Celsius is 0.031 seconds to the negative 1 when the rate constant is 0.1 seconds to the negative 1 at 25 degrees Celsius with the activation energy of 35.8 kilojoules.